Oh boy. All right, last one. Characterizations of invertible matrices. In other words, a theorem, and using that theorem to decide if a matrix is invertible. So this is a lot of our theorems and a lot of linear algebra is saying the same thing in multiple ways, and that's exactly what this theorem says. So this theorem says that if you can show one of these is true, then they're all true. If one of them is false, then they're all false. So we can use this to decide whether or not something is an invertible matrix or not. So if A is an invertible matrix, and if that is true, then all of these other things are true. Or if one of these things are true, then we can say that it's an invertible matrix. So if A is an invertible matrix, A is row equivalent to the n by n identity matrix, which is exactly what we just did up there, right? If I can reduce A down to the identity matrix, then they're the same, right? If A has n pivot positions, so notice this means that I have no free variables. And we can determine whether or not I have no free variables without actually having to do any kind of augmented matrix or anything. So all we need to do is just row reduce that particular matrix and see if we end up with pivot positions in every point or in every column. The equation AX equals 0 has only the trivial solution, right? So that just means that so our homogeneous equation has only the trivial solution, means that it is invertible. That means that the columns of A are linearly independent, which is the next one. The columns of A are linearly independent. If the linear transformation is 1-to-1, we haven't really talked about what it means to be 1-to-1, but 1-to-1 essentially means that your x's and y's don't repeat themselves ever. So like x squared is not a 1-to-1 function because both 1 and -1 map to the number 1. The equation AX equals B, so the non-homogeneous matrix equation, has at least one solution for each B. The columns of A span R to the n, right? So that means that again, if it's in our span, they are linearly independent. The linear transformation maps that onto that. If there's an n by n matrix C such that CA equals I, so again, that's talking about the inverse, or if your transpose is an invertible matrix. So we're going to use this theorem to decide whether or not this matrix is invertible. And the nice, easy way to do this is just to show that we have n pivot positions. So if I just take this matrix and I do a couple of row operations, and basically if I can get these to be zeros and these to have numbers still, then I'm good. That means that I have and essentially what that means is that I don't have any repeated rows here. So we want to make sure that's not happening. We could also take a look and see, make sure that our columns are linearly independent. But I'm going to do a couple of quick row operations, see what we can conclude from this, and go from there. So I'm going to do sort of a couple of things at once. I'm going to try and get rid of the 3 and the 5 at the same time. So I'll do row 2 minus 3 row 1 here, and I'll do row 3 minus plus 5 row 1 here. So that'll give me the matrix 1, 0, -2, 0, 1, 4, 0, -1, -1, which is actually a good sign because notice that those two are not the same. So that was confusing because you might have thought I was trying to switch those. So now I can try and get rid of this one. So all I'm going to do is row 3 plus row 2, and that'll give me 1, 0, -2, 0, 1, 4, 0, 0, and 3, right? And I don't have to go any further. So I don't have to go any further because as you can see, so in this first row, here's my leading entry. There's no other leading entries in that row. So that's a pivot column, right? This one, there's my leading entry. And this one, there's my leading entry, right? So there's no way to actually like get rid of that 3 without causing other things to like appear in the matrix. So because I have 3 pivot positions and I have 3 columns, that means that I am good. So therefore, since number 3 is true from the up there, then we can conclude that number 1 is true. So therefore, A is invertible. And we've proved that it's invertible, and those same operations, right? We would do those same operations to the augmented matrix with the A and the I in it. So we already know like what we're going to do for those. It's just going to modify your I matrix a little bit. So you're part way there to even finding the inverse matrix if you want to. All right, that's it for the week. We made it. Congratulations. Nice job. Proud of you all.